One of the features of Laplace transforms that makes them so useful is how readily they can deal with discontinuous or non-differentiable forcing functions, which is great because engineers like to do things like turn devices on or off. So that has a lot of practical application, and not many other techniques are as adept at handling such problems. So in the last clip, we looked at how the solution for an oscillator is given by this form right here, and how the forcing function ends up giving you this particular solution right here, and that the initial conditions end up giving you the homogeneous part of the solution right over here. So let's take a bit of a closer look at the particular solution, which is often going to be something that you get by convolution. So the way that the convolution theorem works for Laplace transforms is that the Laplace transform of a convolution is equal to the product of the Laplace transforms. So it converts a convolution into a product. And the way that we typically use this is when we're given something that looks like a product and we want to invert it. So we end up with some f times g, and we want to know how do we go about coming back to the land of the t variable. Well, and that's exactly what's going on here with xp. So xp here is the Laplace inverse of the function f times this ms squared plus cs plus k, right? And so by the theorem then, this is going to be Laplace inverse of f convolved with Laplace inverse of this other bit right here, which it's worth noticing comes totally from the data of the device. So if you think of this as something that you built, you've got your mass and your coefficient of friction and your spring constant. All that's internal or intrinsic to the device, and that's what determines what happens there. So then this this part right here, of course, is just f. So you're going to have f convolved with the inverse transform of this, which I'll just call w. So let's see then. Here the convolution, so this is for when you've got functions on the positive half line, then the convolution takes the form integral from 0 to t f of t minus tau g of tau d tau. And so the reason why is when you set up the convolution integral right here, you notice that one of these guys, so namely this one here, this guy is effectively equal to 0 for negative values of tau. So if we were to graph this function g, so say here's what g looks like maybe, okay? And so we're on the positive line right here. If we extend it just by 0 out to the left, then this is what's really going on. So for the point of view of looking at initial value problems, really for g, we're considering g to be h times g, where h is the Heaviside function, or unit step function. Okay. And then now the same thing, or a similar thing, is happening over here for f, but notice that f has been flipped left to right because of the minus sign in front of its argument tau, and then it has been offset by an amount t. So that means that if f, say, originally looked like a decaying exponential, so if this is f of tau, then f of t minus tau is going to look like this. So there's a graph of f of t minus tau for this particular t right here. And so this, I should specify, this axis right here is the tau axis. And so you can see that there's a cutoff right here because we're also thinking of f of tau as being equal to 0 for the negative axis. So this is like h times f. All right, and so this is the reason why when we're doing convolutions for functions of this type, you see that the bounds of integration are from 0 to t instead of from minus infinity to infinity. You can think of them as being from infinity to infinity with these cutoff functions put in there. The other thing that we have that's lovely about the Laplace transform is that if you take the Dirac mass located at the point A, then its Laplace transform, so if we do 0 to infinity, e to the minus st Dirac a t dt, then what we get is, let's see, it's going to evaluate, the Dirac mass is going to evaluate its argument, so that's this one right here, where t is equal to a. And so as a consequence, you just get e to the minus as. And then the other thing to notice is that this occurs precisely when a is when t is in the interval from wait, no, hold on, did I do it backwards? T is in the interval from 0 to, yes, I did it wrong. When a is in the interval from 0 to t. If t is less, then we don't get anything. So this is actually multiplied by the cutoff located at a. And then if we look at the special case when a is equal to 0, which we usually just write delta 0 as delta, then this one is going to give us e to the 0, which is 1. Or if you want, you can think of this just as the unit step function, since we're on the domain from 0 to infinity. Okay, so that means that if I take my forcing function to be delta, and we take Laplace transforms, then the Laplace transform of my forcing function is just the constant function 1. Okay, and so that means that if I go back to the original example that we were looking at, and we have that f is equal to the Dirac delta, then that means that our corresponding particular solution is going to be Laplace inverse of, and then my numerator is just 1. And so this is actually my fundamental solution W. And so this is the so-called unit impulse response. So you slap the spring with the Dirac delta, bam, and then you watch how it bounces around, and the answer is exactly this thing that we get right here. And the lovely thing is that can be actually recorded in a lab empirically just by measuring the outcome of what happens when you slap the box. So you can experimentally determine the unit impulse response. And that has lots of interesting applications.